Hi everyone. In this video, we are going to explore about the interfacing of PIC18 microcontroller. In that, we see that ADC interfacing. ADC interfacing, we are using temperature with LM35. In this presentation, we are going to explore about the analog to digital converters. It will bridge the gap between physical sensors and digital systems. ADCs are essential for automation, monitoring and control and sound synchronization also. First we see about the input or introduction about the analog to digital conversion. We know that our physical world is analog with continuous signals. For that we are using temperature, pressure and lights are the examples of analog values. For best example, we see that the medical thermometers show direct continuous values. Digital systems need to interpret these physical values. So ADCs translate continuous analog signal to discrete digital data. The LMS35 temperature sensor. The LMS35 is a precision centigrade temperature sensor. Its output voltage directly reflects in Celsius temperature. So it has sensitivity of 10 millivolt bar degree Celsius. For example, 25 degree Celsius outputs for 250 millivolt. It operates from the range of minus 55 degree Celsius to plus 150 degree Celsius with plus or minus 0.5 degree Celsius accuracy at the temperature of 25 degree Celsius. It requires 4 volt to 30 volt for power supply. So first we see about the fundamentals of ADC. So converts voltage. So the ADC transforms the analog voltage into digital number. The next characteristic is resolution. A 10-bit ADC provides 1024 distinct values, that is 0 to 1023 digital values. Reference voltage, V reference sets the conversion scale, for example 5 volt. Sampling rate, it determines how frequently conversion occurs during ADC conversion. In this, we see that the ADC registers. The ADC registers are main two registers available, that is a ADC on 0 and ADC on 1. ADC on 0 register, it controls ADC operation, and ADC on 1 register, it configures ADC pins and voltage references. In AD on bit, it enables the ADC module and it has a 8-bit analog input channel, that is AN0 to AN7. And the pin is a go bar done bit. It starts and indicates conversion status. PGFG bits, it configures specific pin as an analog or digital input or output. VCFG bits, it selects the voltage reference, that is V reference plus and V reference minus, because we know that the temperature sensor gives the minus 55 volt degree Celsius to plus 150 volt degree Celsius. Common V reference settings, that is a VDD and VSS ground. In this diagram, we show that this shows the V reference or A input signals, and this is the voltage reference IRR signals. And ADC conversion formula, the combined formula is digital value. We know that our output is a digital value. So digital value is equal to temperature in degree Celsius into 0.01 into 1023 bar V reference. And LMS output, LMS35 output V in is equal to temperature in degree Celsius into 0.01 volt per degree Celsius. The third one is a 10-bit ADC output, that is digital value is equal to V in divided by V reference into 1023. We know that our reference value is a plus 5 volt. So the formula will simplify to digital value is equal to temperature in degree Celsius into 2.046. For ideation, we are calibrating for specific ranges in ADC. So design task is calibrate LM35 and pick ADC for a freezer. And target range is a minus 20 degree Celsius to 0 degree Celsius for freezer applications. Challenge: LM35 outputs negative voltage for negative temperatures. So solution: consider a voltage divider or offset circuit for input conditioning. So the optimization is optimize V reference for enhanced resolution in narrow ranges. So the prototype are simulation and display. So interface LM35 temperature sensor to PIC microcontroller such as PIC16F877A. So for simulation software we are using Proteus or MPLAB XID with simulator. LCD for display we are using LCD display show converted temperature in degrees Celsius on an LCD screen. The real-time monitoring is observe temperature fluctuations as they occur. And for testing phase, where conversion calculation is a 30 for target temperature and LM35 output is 0.3 volt and the digital value approximately reading is a 61. So the question part is, what is the 10-bit digital value for 30 degrees Celsius if V reference is equal to 5 volt? We know that output voltage is equal to 30 degrees Celsius into 0.01 volt degrees Celsius equal to 0.3 volt. So the digital value is equal to V in by V reference into 1023. So it is a 0.3 volt divided by 5 volt into 1023 is equal to 61.38. The result is the 10-bit digital value would be approximately 61 integers. The conclusion part, bridging analog to digital. Accurate sensing, the LM35 offers precise low-cost temperature data. Core understanding, mastering registers and formula is vital one. And enables control, it allows precise digital monitoring of analog signals. The fundamental is ADC interfacing is key to embedded systems. Thank you.